All right, let's continue our discussion of limits with three-dimensional graphs. And let's look at limits at boundary points. So we've looked at limits of points that are in the domain, and that's pretty easy. We can just use direct substitution. But what if we're looking at a boundary point, and that point is not in the domain? Suppose P sub 0, AB, is a boundary point of the domain of F. Okay, let's just stop right there. So let's say we've got some function here, and here's our domain. Remember, our domain lives in R2. And so P sub 0 is on the boundary of this domain. Okay, this is a picture here, but I kind of like this three-dimensional picture. So we've got that. The limit as xy approaches AB of f of xy exists, even if P sub 0 is not in the domain of f, provided f of xy approaches the same value as xy approaches AB along all paths that lie in the domain. All right, let's unpack that a little bit. So let's say I've got this domain here, and let's say this is an open set. And we talked about that earlier. In other words, it doesn't include its boundary points. Let's say the boundary points are not in the domain, okay? This is dotted. But so P sub 0 is on the boundary but not in the domain. Let's say that's happening. And we want to look at the limit as x, y approaches P sub 0 of f of x, y. So what we need to look at is what happens as xy gets close to P sub 0. What happens as xy approaches P sub 0? Well, there's a lot of ways that xy can approach P sub 0, right? This is where it's much different than Calc 1. We could approach, on this path this way. We could approach P sub 0 this way. We could approach P sub 0 this way. There's lots of ways to approach P sub 0. Now let me do these in different colors. So let's say I approach P sub 0 this way. Now I need to look at the surface up here. Let's say right here is, well, I'm not going to call it f of P sub 0 because P sub 0 is not in the domain. But let's just say I've got this point up here. I'll just leave it like that. And if I take this path, now all the points on this path are in the domain. So let's say I project that up onto my surface and it creates some path like this, okay? And it's headed towards this point. So now let's say I come down here and I do a different path from xy approaching P sub 0, and then I project those red points, the outputs of those red points, up on my surface, and it looks like that. Okay, and I go on this path here, and I approach P sub 0, and I project those points up here. All right, so these are the outputs up here. Now, if these outputs are all approaching the same point, let's call this point z sub 0. Even if z sub 0 is not on the surface because P sub 0 is not in the domain, the limit would still be z sub 0. If every path approaching P sub 0, if the limit as xy approaches P sub 0 along every path, this limit also approached z sub 0, then we could say that the limit as xy approaches P sub 0 of f of xy equals z0, even if P0 is not in the domain. Okay, what's an analogous situation in 2D? We don't really need this. Let's get rid of this. Remember the situation where we had like some graph and it had a hole in it. It's going along like this and it's got a hole in it. So this is just 2D, right? This is like y equals f of x. Okay, at this a value, there was a hole. So a is not in the domain of f of x. But we said, hey, if the limit as x approaches a from the right of f of x equals the limit as x approaches a from the left of f of x, and let's say this y value is L here, and let's say both those limits equal L, then the limit as x approaches a of f of x equals L, even if a is not an element of the domain. I'm going to go is not an element of the domain. Even if a is not in the domain, the limit still exists if the limit from the left equals the limit from the right. So this is the analogous situation in 3D. It's just that there's more than two ways that we can approach a. In this situation, we could only approach from the left and the right, so we had to check both of those. In 3 dimensions, we have to look at every single path, and there's an infinite number of paths and ways that we could approach p sub 0. So you're right in thinking, how am I going to check infinitely many paths? You're not. So we're more going to use this to prove that something that the limit does not exist. If we could show, for example, that, hey, if I take this red path, I head towards z sub 0. And maybe if I take this blue path, I head towards z sub 1. And they're both approaching p sub 0. Both of these paths are approaching p sub 0, but the outputs are approaching different values. Then we're going to say, okay, that limit doesn't exist. And that analogous situation in 2D would be if you had like a jump discontinuity. Right? You say, okay, well, the limit as x approaches, a from the left is different than x approaches a from the right, so therefore the limit doesn't exist. That's what we're going to do down here. We're going to look at two different paths. Okay, so we will get to that. That's going to be important. So here where I said, what's the analogous statement for f of x, a function of one variable? That's this business right here. All right, that's this business here. Okay, now let's look at a couple examples of finding limits where the point is not in the domain. So let's start off with question number 1 here. It says, what is the domain of f of x? So why don't you take a second and write that out. Think about that. All right, hopefully you're saying that x plus y cannot equal 0. So therefore, y cannot be the opposite of x. Does the domain of this function have boundary points? Well, it does. So if we graph this domain, we could graph the line y equals negative x, but make it dotted because y can't equal negative x. So that's the line y equals negative x. And then the domain of this function would be anything that's not on that line. All right, so y equals negative x would be a boundary point, because if I pick a point on y equals negative x and I draw a disk centered at that point, then that disk is going to contain points that are in the domain and points that are not in the domain for every disk that I draw. So the points on this line would be considered boundary points. And one of those points is negative 1, 1, which we see right here in the next question. So negative 1, 1 would be like right there, right? Okay, so we want to evaluate that limit, but that's not in the domain, so I cannot use direct substitution. Well, we could think about this path business, and we're definitely going to do some of that stuff with the paths. But we want to use a technique here, or think about trying to use a technique that we used before, which was, can I simplify that? Maybe I can algebraically manipulate this so that I can do direct substitution. So is there a way we could factor the numerator? And the denominator is x plus y, so really all I care about is, can I factor it with a factor of x plus y, so those will cancel. Can I factor it like this somehow? How's your factoring skills? All right, it does factor, so it's going to be 2x times x is 2x squared, and then y, that would have to be negative 3y to get negative 3y squared, and then that would be positive 2xy minus 3xy is negative xy, so that is the factorization. So if I can simplify f of x, f of xy, then I don't have to do this path business just quite yet. So I could rewrite that as the limit as xy approaches negative 1, 1 of, and then I could factor this out and cancel. And then try direct substitution. So that gives me the limit as xy approaches negative 1, 1 of 2x minus 3y, which I can do direct substitution, 2 times x minus 3 times y. And that's what, negative 5? Higher mathematics. Okay, so I didn't have to like prove every single path approaches this point, but it would be true that if I looked at every path approaching the point negative 1, 1, that the outputs are going to approach negative 5. The outputs on that surface are going to approach negative 5, even though it never is negative 5. Like f of negative 1, 1 is not negative 5 because it's not in the domain. That point doesn't exist on the surface, but everything approaches that point on the surface. So the next part is asking us to write a formula for the line that lies on the plane that contains f of xy but is not in f of xy. Let's go take a look at that line just to get an idea of what we're being asked to do there. So here's our plane right here. Okay, there's our plane. Now notice here's the reduced fraction version of our plane. I could turn that on. Okay, that's the same plane. I'm afraid to turn this thing once I start turning. Okay, there we go. See, it's the same plane. It's showing us a little bit more of it. And then we have a line that's on the plane. Remember, we have y cannot equal negative x. So if we picture y equal negative x lying in the xy plane, all the points above that line that lie on the surface of this plane are not in the domain. But, you know, this technology can't really show us that. So where's the line y equals? So here's positive x, here's positive y. So y equals negative x would be like this line right here. Okay, then on the plane, all the points above and below that do not exist. So there's some like dotted line on this plane where there's no output points because x plus y equals 0. So we want to figure out what that line is. All right, so what do we know about that line? Well, we know that line has to lie on the plane, right? So the plane, the whole plane itself can be modeled by our reduced version, 2x minus 3y, this business right here, 2x minus 3y. So the plane is z equals 2x minus 3y. Now the place where we don't have really any existing points is, so let's say points do not exist on the plane when x equals negative y, or let's say negative x equals y, same thing, but we'll just do that. All right, so what we want to do is combine these two ideas together, and we're going to substitute, and we're going to take, let's do negative x and put that in for y over here. So if negative x equals y, which causes us to not have any outputs, then we'd have z equals 2x minus 3 times negative x, or z equals 5x. So in other words, the z value is 5 times the x value. All right, so if we think about this line, let's write this line as a vector valued function. That might be a nice way to do it. Okay, so what's the x value? Well, the x value is just x. What's the y value? Well, if I use this relationship right here, my y value is going to be the opposite of x. And then my z value would be 5 times x, which I found over here. Okay, let's go take a look at that. So I've got that input right here. As a parametric equation, we have that our line goes through 0, 0, 0, because this plane goes through 0, 0, 0, and then it's parallel to this vector 1, negative 1, 5. All right, so there's my line right there. Now, where's my limit point? I could turn that on right here. Here's my limit point. So if I look as xy approaches 1, what was it, 1, negative 1, or negative 1, 1? It was negative 1, 1. Then my output will approach A, even though this whole line right here on this equation right here does not contain any outputs, right? If I use this equation right here, then this is like a dotted line. I couldn't figure out how to make it dotted, but this is a dotted line because there are no outputs there. But the limit is going to approach negative 5, which is where this point A is at negative 1, 1, negative 5. All right, let's look at one more example. And this example, like the last example, is one that we'll be able to manipulate algebraically. And we have this property: if a function can be algebraically manipulated so that direct substitution yields a resulting limit, then the limit exists and it's the result of direct substitution. So one technique that you've used hopefully multiple times is the whole idea of factoring and canceling, which we used in the last example. Another very common example and way to simplify functions involves a square root. Do you remember what we could do with that? It involves using the conjugate. So the conjugate of, say, square root of a plus b is square root of a minus b. Or b minus square root a is b plus square root a, something like that. So what we want to do is multiply the top and bottom of this fraction by the conjugate of whichever expression contains the square root, which in this case is the numerator. So the conjugate of the square root of x plus y minus 3 is the square root of x plus y plus 3. And this is perfectly legal to multiply the top and bottom by something. So why don't you pause the video, crank out that algebra, and see if anything wonderful happens. So when we FOIL out the numerator, we get this thing that happens when we multiply by a conjugate, is that the middle terms end up dropping out. The plus 3 square root x plus y and the minus 3 square root x plus y, which is sort of why we do it. Now, one of the keys to this technique is to not multiply out the non-conjugate product. All right, these are not conjugates here. Don't multiply that out. Because the whole deal is we're trying to get this denominator to cancel out. And actually what I should have done before we started this is tried direct substitution. I mean, you should always do that because there's no reason to do this algebraic stuff if direct substitution is going to work. So if we put, oh, that's too sloppy. If we just substitute in 4 for x and 5 for y, right? What happens in the denominator? We get 4 plus 5 minus 9, that's 0. So we cannot use direct substitution, which is why we're trying some algebraic manipulation. So by multiplying by the conjugate in the numerator, I'm just going to end up with x plus y minus 9. And this is why I don't want to FOIL out or multiply out the denominator, because I'm trying to get this factor of x plus y minus 9 to cancel. Why do I want that factor to cancel? Well, because that's the factor that's causing me a 0 in the denominator, which is causing me sadness. We don't want that. So now this whole factor will cancel with this whole factor, and we're just left with 1 over the square root of x plus y plus 3. Now let's try direct substitution. All right, so I get 1 over the square root of 4 plus 5 plus 3. This is looking lovely, which is going to be 1/6. So even though the point 4, 5 is not an element of the domain of f of xy, the limit as xy approaches 4, 5 does exist. Matter of fact, it's 1/6. So if you were on the surface, the z values are approaching 1/6 as the xy in the domain get closer and closer to 4, 5. Then the outputs get closer and closer to 1/6, no matter what path you're taking as you approach 4, 5. All right, so we're going to stop there, and in the next examples, we will look at proving that a limit does not exist by examining two different paths towards the point and showing that those two different paths lead to a different output for your limit.